Alright, in this video we are going to be talking about Module 8. We're going to be getting into inverse functions. So as usual, I will go through the notes, and then at the end I will work through the homework problems and the problems that you need to look out for on the test. So starting with 8.1, we are going to identify whether a function is one-to-one and invertible. So it says right below that a function is one-to-one if both the function and its inverse are functions. So this can be found if different values of the domain correspond to different values of the range for both the function and its inverse. Examples, it says example 1, f of x equals 2x plus 5, and it says no matter what value x is replaced with, a different y value is produced. Different values of the domain correspond to different values of the range. Therefore, the function and its inverse are one-to-one. If you look at the next one, it has an example of what is one that is not one-to-one. So f of x equals x squared. It says if you replace x with 2, y equals 2 squared, which equals 4. If you use -2, then -2 squared also equals 4. So it says that the different values for x produce the same value for y, or different values of the domain produce same value on the range. Therefore, the function and its inverse are not one-to-one. So you can use the horizontal line test. A function is one-to-one if every vertical and horizontal line intersects the graph of function at most once. And then it also says something below here. In general, a function that is either increasing or decreasing on its entire domain must be one-to-one. So there is an example. It says no matter where you draw a vertical line, you can cut the graph only once. And then no matter where you draw a horizontal line, you cut the graph only once. So therefore, this is a one-to-one function. The next one is an example of what is not a one-to-one function. It does not pass the horizontal line test. For 8.2, we are going to find inverse functions. Given a set of ordered pairs, we'll find the inverse of the function. Given two functions, we will determine if they are inverses of each other, and then we'll be given an equation and be asked to find the inverse. By the defining of inverse function, the domain of the function is the range of the inverse. And the range of the function is the domain of the inverse. So there is an example. If the function is defined by the following, is one-to-one, find the inverse. So they give us 3 points. We have our domain, and then we have our range. The inverse function, we would exchange the x's for the y's, and we would end up with the points 0, 3, 1, -5, -2, 0. And then our domain and our ranges would be swapped. So by definition, the function and the inverse are one-to-one. So another example like that. Down here it says that inverse functions, let f be a one-to-one function. The g is the inverse of f. If f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. The condition the f is one-to-one in the definition of inverse functions is essential. Otherwise, g will not define a function. All right, so what is this saying? we are given f of x and g of x. We want to determine if they are inverses of each other. So we need to find, we can use f of g of x equals and solve it this way. And we can do the same thing, g of f of x, and solve for x. We end up with x at the end. Therefore, since those are equal, they are one-to-one inverses. Finding an equation of the inverse. For a one-to-one function f defined by an equation y equals f of x, find the defining equation of the inverse as follows. So it gives us some steps. If necessary, replace f of x with y. First, interchange x and y, and then solve for y. At the end, you will then replace y with the inverse for our f of x. So here's an example. They give us what f of x is. We are going to change f of x into y, so we get that y equals our function. We are then going to swap out our x's and y's. X equals, and then we will solve for y. So this, our inverse, would replace, and that would be our answer. So there are some more examples on that at the end of that. 8.3 is the last lesson for Module 8, and we are going to graph the inverse functions. So it is given that we have our f of x, the inverse was found, and then the graph is of both of these functions. So the inverse graph is the reflection of the graph across the line y equals x. So if the two graphs reflect across the line for y equals x, then they are inverses. So here's another example. All right, so as always, I will look at the homework questions that you need to look out for on the test. So number 2 on 8.1, it says determine whether the function graph is one-to-one. So remember, in order to be one-to-one, it has to pass the vertical line test and the horizontal line test. So we can tell off the bat this one is not one-to-one because it does not pass the horizontal line test. So it's going to be A or B. No, there is a horizontal line that intersects the graph at more than one point. Okay. Perfect. That was number 2. I'm not going to look at 3. I'm not going to look at 4. So that is it for 8.1. For 8.2, I'm going to look at number 3. So this is 8.2, number 3. And it says, if the function defined by the following is one-to-one, find its inverse. And so we are given 4 points. We have 4, 1, 2, 2, and 1, 8, and 5, 1. So if we look at our notes for 8.2, it says that by the definition of inverse function, the domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. So we're going to find our domain and range, and when we swap them, that will be our inverse. Okay, so let me look at this. So when we are finding our domain, we're looking at our x's. So our domain is going to be 4, 2, 1, and 5. The range is going to be 1, 2, 8, And then at the end, we have another one. We are not going to list that. For our inverse, we are going to swap the points. So we get 1, 4, 2, 2, 8, 1, and then 1, 5. And then our domain for the inverse is 1, 2, and 8. We're not going to do the 1 again. And then the range is 4, 2, 1, 5. So the function is not 1 to 1. I'm also going to look at number 4. It says, for the function f of x equals 7x minus 9, determine whether f of x is 1 to 1. If so, write an equation for the inverse function in the form of y equals, and then we're going to graph them both and then give the domain and range of both. If the function is not 1 to 1, just say. So remember the steps. We are going to set this equal to y. We're going to change f of x to y. And then we are going to swap the x and the y. After we swap them, we are going to solve for y. So I'm going to move 9 over, and I get 7y equals x plus 9. And then I'm going to divide by 7, and I get that y equals x plus 9 over 7. I can now change this back, x plus 9 over 7. So how do we know if this is 1 to 1? So there are a couple ways. If we find our domain and our range of the function and its inverse, we can use the logic that we used on number 3 to determine if it's 1 to 1. We can also graph the functions. So I have y equals 7x minus 9, and then I'm going to have x plus 9 divided by 7. So I'm going to graph both of these, and I can see that they do look and appear to be 1 to 1. If we were to use the line where y equals x, and if we see that these are reflections over that line, we can easily see that yes, the function is 1 to 1. And our inverse equals, so I'm going to create a fraction, and I have x plus 9 divided by 7. All right, so we have a graph, and we know that it is over here, so it has to be A or C. It's not D because this is saying the function is not 1 to 1. It's not B because this graph is down here in our 4th quadrant, and we need the intersection to be in the 1st quadrant. So let me look at A and see what we're looking with here. So I'm going to click on trace. Remember our nifty little tool. And it's not giving me the intersection point. Let me zoom in. I'm going to do 0. And then 0. So I kind of zoom in. So it's not really crossing at, it looks like it's like 1.5 and 1.5. So let's look at our graphs. So this is not correct because it looks like the one of our lines is not correct, the inverse. So that was A. Let me look at C. So this one looks correct. So it is going to be option C. All right, give the domain and range of the function and its inverse. Begin by finding the domain and range of f of x. All right, so let me zoom back out. And we can see so we can see that the domain of our function is going on and on and on. So it appears that it is going to be negative infinity to infinity. And then the range of our function is also going to be negative infinity to infinity. For our inverse, same thing. All right. Number 5, determine whether the function is one-to-one. If so, write an equation for the inverse. And then we're going to graph and then give the domain and range. So very similar to what we just did. So I'm actually not going to do number 5, but this is a question. There is a test question like this on your assessment. And the assessment for Module 8 and 9 are going to be combined. Let me look at number 6. So it says determine if the function is one-to-one. If so, okay, so same thing that we have been doing. We just have a little bit more difficult function that we're working with. So number 6, f of x equals x plus 7 over x minus 3. All right, so we're going to do the same thing that we just did. We're going to set this equal to y. Is you want to swap your x's and your y's. So we get x equals y plus 7 over y minus 3. And we now want to solve for y. Get rid of this fraction. I'm going to multiply both sides by y minus 3 so that I can cancel this out over here. And I am left with x times y minus 3 equals y plus 7. And I'm going to distribute my x. So I get xy minus 3x equals y plus 7. And I want to get y's on one side, so I'm going to move our 3x over and cancel these out. And then I'm also going to move my y over. So I end up with plus 3x over here and then minus a y over here. So I have xy minus y equals 3x plus 7. So we have our y's on one side. Both of our terms have a y in it. So I can pull the y out, can factor this y out, and I get x minus 1 equals 3x plus 7. So basically we can work backwards. We can divide by this x minus 1, and we now have y by itself. equals 3x plus 7 over x minus 1. So yes, our function is 1-to-1. So let me plug both of these into our calculator. I start out with y equals x plus 7 divided by x minus 3. My inverse is going to be, I have parentheses, so I have 3x, I have 3x plus 7 divided by x minus 1. Graph. All right, so we do have a reflection. All right, so we do have a 1-to-1 function, and then our inverse equals 3x plus 7 divided by x minus 1. All right, let's look at our graphs. So let me see, where's my calculator? So it's not B. It's either A or C. It doesn't look like it's A either, so it is C. And then our domain and our range of our function. So our function is the blue one. And we can tell just by looking that it does appear to be from negative infinity to infinity, but we know that on our function that x cannot equal 3 because we can't have a 0 in our denominator. So that is why we have a disconnection in our lines on our graph, because x cannot equal 3. So our domain is going to be negative infinity to infinity minus the 3. So we stop at 3 and union, and then we go from 3 to infinity. Okay. And then the domain of our inverse, x cannot equal 1. So similar, so we go from negative infinity to 1, and then 1 to infinity. All right, for our range, so our range of our function is going to equal the domain of our inverse. So the range is going to be negative infinity to 1, and then 1 to positive infinity. Okay, and then the range of our inverse is going to equal the domain of our function, which is this, negative infinity to 3, and then 3 to positive infinity. Negative infinity to 3, and then 3 to infinity. All right, so there is a question like that. All right, so number 8 is the last one we're going to look at on 8.2. There is going to be a question like this on your test. All right, so number 8, it says, for the following function defined that is 1-to-1, write an equation for the inverse. Okay, so it tells us that it's 1-to-1 and they give us a function. f of x equals the square root of negative 2 plus x, and then it tells us that x is greater than or equal to 2. All right, so we're going to do the same thing. We're going to set our f of x equal to y, so y equals the square root of negative 2 plus x, and then we're going to swap. X equals the square root of negative 2 plus y, and we want to get y by itself. So to get rid of a square root, we are going to square both sides, because when you square a square root, they basically cancel each other out. So if I square this, that cancels out, and I'm just left with what is inside, which is negative 2 plus y. And to get y by itself, I'm going to add 2 to both sides, and I get that y equals x squared plus 2. And remember, we have to change our notation to represent the inverse function, and x is going to be greater than or equal to 0. So let me write that. X is greater than or equal to 0. So I've got x squared plus 2. Well done. Okay, so, oh, that's not all of it. So we're going to graph everything. So just like you were doing previously, graphing and finding the domain and range, you're going to do that for this. I'm not going to do it on this homework question, so just make sure you practice this. Continuing on with 8.3, the homework questions to look out for that are going to be on the test. Number 1, we are going to graph the inverse of the given one-to-one function. So they are giving us a function on a graph. It does need to reflect over this black dotted line where y equals x. So if it reflects over that, it would need to be coming up over here somewhere. So let's see what we have for our options. It's not going to be 10. It is staying in quadrant 1, so we need something like that. It's not A, it's not B. B is reflected over the x-axis. I'm sorry, yes, the x-axis. A is reflected over our y-axis. C looks like it's taking the y equals x line. And then D is going to be our correct answer. This is the one that is reflecting over that dotted black line. All right, so there's a question like that. This appears to be the same question. Okay. So 1, 2, and 3 all appear to be the same question. Number 4, number 5, number 6. So I'm not going to look at any. These are all very similar. I'm not going to look at any of these questions. Module 9, we're going to be talking about exponents and exponential functions. So an exponent is whenever you have like x squared, x cubed, x to the 4th. So in this case, they represent with a to the x, and x is going to be our exponent. It says that the base is a. So it gives us some a to the negative n equals 1 over a to the n. So these are two properties that you're going to be using. There are some examples. And as always, I will look at examples. I will look at the homework questions, the questions that you will need to look out for on the test. So characteristics of the graph of f of x equals a to the x. This is helpful information. It says the points -1, 1 over a. 0, 1, and 1a are on the graph. So that is something that I'm going to highlight. If a is greater than 1, then f is an increasing function. If a is a fraction, so if it's in between 0 and 1, then f is a decreasing function. The x-axis is a horizontal asymptote, and then the domain and the range. And then these are some of your typical exponential functions, the graph. And then we have translations, so shifts, reflections. These are just some examples at the bottom. And then 9.3, we are going to apply exponential functions. And then 9.3, the applications, we're going to apply the exponential functions. And we're talking about compound interest. It gives us the formula for compound interest. And then continuous compound interest. So they're going to give you all of the pieces that you need for the formula. You just plug everything in and then you can put it in your calculator to find your answer. And then there's some examples at the end. So let's look at our homework for Module 9. All right, so questions to look out for the test on Module 9. Remember, Module 8 and Module 9 assessment is going to be combined. So 9.1 homework, we are given a function and you're going to be plugging in a given value for x. So I'm not going to do 1, 2, 3. I am going to do number 4. So we are given a value for g of x, and then we want to find the value where x equals -2. All right. Okay, so 9.1, number 4. And they give us that g of x equals 1/9 to the power of x. And we want to find where x equals -2, but they give it to you like this, g of -2. So g of -2, we are going to plug in -2 for x. We get 1/9 to the power of -2. So when you're looking at this, this -2 basically is going on to both of these. So we have 1 to the -2 and then 9 to the -2. 1 is just going to be 1. Since we have 9 to the -2, we can flip this and get rid of our negative exponent. If you look at your notes, a to the -n is the same as putting 1 over the a to the positive n. If we have -n in the bottom, we can still switch it and it becomes n squared, which is just 81. Now you can put this into your calculator. Your calculator, you would just do, you can do it starting straight from the beginning, 1 divided by 9, and then your exponent, you'd put -2, and it would give you the correct answer. So our answer is 81. Great. So there is a question like that. Not going to look at 5. So we are also going to look at number 6. So number 6, gives us that 16 to the power of x equals 4. And we need to find our solution set. So we're going to solve for x. We are going to solve for x. So there's a couple of ways. So let's rewrite this where our bases are equal. Right now our base on the left is 16 and then the base on the right is 4. If I rewrite 16 as being 4 squared, then we have the same base. So this becomes 4 to the 2x equals 4, and over here we just have to the power of 1. Anytime you have a number to the first power, it equals itself. So now we can set 2x equal to 1, and we find that x equals 1/2. All right, so you will have a question like that, and also like this one. So number 7, 3 to the 2x minus 3 equals 81. So this one is similar to what we just did. We need to get the same base on both sides. So if we have 3 to the 2x minus 3 and then 81, we need to find the root of 81. So we know 3 squared is 9. 3 cubed is 27. So let's try 3 to the 4th and we get 81. Great. So 3 to the 4th is going to be equal to 81. Now we can set our exponents equal to each other. 2x minus 3 equals 4. Okay, and now we can solve for x, which gives us that x equals 7/2. It doesn't specify how they want the answer, so I'm assuming. All right, and then let's look at number 8 as well, because you will have another question that will be like number 8. So this one is also super similar. 64 to the power of 5x equals 16 to the power of x plus 3. So this one does make it a little bit trickier because our bases, we are going to have to manipulate both of our bases. So 16 squared does not equal 64. You can put that into your calculator, 16 squared, and it gives us 256. So we know that we're going to have to manipulate both of our bases. So 4 is a number that goes into both of these. 16 is going to be 4 squared. And then, so 4 cubed, and then we have 5x. All right, so your exponents will go together. 3 times 5x is 15x. And then 4, so 2x plus, so 2x plus 6, because 2 times 3. All right, so our bases are equal, so now we can set our exponents equal to each other. 15x equals 2x plus 6. I can subtract 2x from both sides, and I get 13x equals 6. I can divide both sides by 13, and I get that x equals 6/13. Alrighty. And then number 9, this is also going to be on the test. So it says solve the equation r to the 6/7 power equals 64. Alright, so let's look at our notes for 9.1 and look at the properties that we are given at the very beginning. It says a to the m over n equals, and we're going to use n as our root, and then m stays as our exponent. So I have r to the 6/7. If I multiply by the exponent 7/6, these will cancel out. Remember, whatever I do to one side, I have to do to the other. So we end up getting 64 to the exponent of 7/6. And then we are just left with r over here. So I can use that property where we have a to the m over n equals the n root of a to the m power. So basically we can rewrite 64. We have this. So it's not the square root. It is going to be the 6th roots of 64. And then have the exponent of 7. And that is going to equal r. Whenever you put this into your calculator, now if you did want to put this in your calculator, you can just leave it as 64 to the exponent of 7/6. So if I have 64 and then use our caret to get the exponent, I could just put 7/6 in that exponent. And it'll give me my answer. And if that, I know it's kind of confusing, you can also do 64 to the 1/6, and that will just tell you what the root is, which is 2. You can now put 2 to the 7th power, and it gives you that same answer. So you can put everything in at once. So I'm going to do plus or minus 128 because it can be positive or negative. So don't forget that. Okay, and I'm not going to do number 10. Let's look at 9.2. All right, for 9.2, I'm going to look at number 1. It says to graph the equation y equals 12 to the power of x. So you will have a test question like this. So if you look at your notes, it has the characteristics of the graph of a of x, and it gives us different things that we can look at. It says it will have the points on the graph, -1, 1 over a, and then 0, 1, and 1, a. So in this case, our a is going to equal 12. So we're going to have the point -1, 1/12, 0, 1, and 1/12. So let's look at our graphs that we have over here. And also, like, we know it's not a straight line. We know it's not going to be B, or whatever this one is. It's not going to be X. It's not going to be a parabola. So it's going to be something like these two right here. So we have the point 0, 1. Let's look at this one. We have the point 0, 1, okay. That's not on this one. And then 1, 12. Okay, so that was that one. Let's look at this one. Okay, so here we have 0, 1. So yes, this is it. And then we've got 1, 12, which is going to be up here. So it looks like it's going to be this graph right here. Okay, you have a question like that. You will have a question like number 2 where you have to graph this one. So in this case, a equals 1 over 5. So 1 over, if our first point over here, -1, comma, 1 over a, you would put 1 over 1/5, which turns into 5. So we're looking for -1, 5. Okay, it's probably not going to be this one. Let's look at our first graph. We want the point -1, 5. Okay, so it looks like this has that point. It also has 0, 1. And then it has 1, 1/5. Okay, so actually looks like it's this graph. Great. I'm not going to look at 3 or 4. 5. This is the one that we just did on number 2. But yes, there is a question like that. And then number 6. So they're going to give you the function, and then you have to graph it, and then give the domain and the range. So let's look at this one. We have 3 to the x, and then plus 3. So if you look at your notes, they do have examples of some graphs. This one is going to be where the graph is translated or shifted up, because we have that plus 3 graph. This is 9.2. Number 6, f of x equals 3 to the power of x plus 3. And we're going to have our XY table. For x equals 1, f of 1 equals 3 to the power of 1 plus 3. So I've got 3 plus 3 equals 6. Okay. Let's do, I can also do 0. That will be a good one to figure out a point that's close to the origin. Okay, that's going to be 0 plus 3 equals 3. So I have a couple points that I can start with. Let's click on our graph. We know that it's going to be this, we're going to use this exponential tool. And I'm going to start with our first point, or I'm going to start with our second point, 0, 3. So it does pop all of this up. It does. So our base is going to be 3. We do have a shift, a vertical shift, and it is going up 3 points. Okay, that is the only thing that's going on. So I'm going to click save, and it looks like, okay, everything is good. Great. And then you're going to put in the domain of the function and the range of the function. Not going to go over that. And that is all the ones that you're going to be looking out for 9.2. Let's look at 9.3. 9.3 is over the compound interest formula. There's only 5 questions that is on that. I am not going to do one of these as practice.